You've heard about clouds, you've heard about automation, and you've definitely heard a lot about AI recently. We're going to be putting all of those things together today in this quick demo. I'm James Kelly from Juniper Networks. I'm going to be talking about setting up and automating the design of AI clusters with Juniper Apstra and the new Terraform provider for Apstra. Let's get into it. All right, let's start in our browser by looking at this repository on GitHub. This is the Terraform Apstra examples repository under the Juniper organization. This is accessible and open to everyone. Here you'll find many examples and a growing list of them as well of things that you can automate inside of Juniper Apstra, which is, of course, I should probably explain, Juniper Networks intent-based management tool for data center fabrics. It's also multi-vendor and very well known for that. Terraform is obviously an infrastructure as code automation tool, and the Terraform provider for Apstra allows you to drive Apstra and hence your data centers through Terraform. And one of these kinds of data centers that I mentioned in the opening is AI clusters. In AI clusters, there's some differences to the fabric design. And of course, Apstra lets you customize fabric design. But rather than a customer, say, starting out with having to design their data centers, we have many examples that we put together for different sizes of AI clusters that you can just apply to Apstra in a matter of a few seconds with Terraform. And that's what I'm going to be showing you guys today. So one of the subfolders of this repository is AI clusters. And a few people, including myself, have put together this automation to do these examples and make, as I said, various sizes of clusters easily creatable inside of Apstra in terms of the design. So you'll find a whole bunch of things here in terms of all of the steps that you would need. One of the very first things you'd want to do is, of course, install Terraform if you don't have that, say, on your laptop. There's ways of using Terraform Cloud that is explained in some of the other examples. I'm not going to show that today. And beyond that, you also need an instance of Apstra. Now, you might already have Apstra running in your data center, but rather than having to install or set up an instance of Apstra, one of the easy ways you can access Apstra is through Apstra Cloud Labs. You can easily start a topology here for free. This is open and accessible to everyone. When you do that, you can pick an expiration time, and after a few minutes, it will spin up an instance of Apstra and a topology. Now, in my specific sandbox in Apstra Cloud Labs, I elected to just do an Apstra-only instance, so there's no actual physical devices. Since I'm just going to be showing the automation of the logical design today, I don't need any physical boxes. And you can see that there's a simple button here, open a new tab, that'll allow you to log in. So I'm going to log in with the password that it provided here, and the username admin, of course. Now, this is a fresh instance of Apstra that I really haven't done anything to. And its welcome screen here actually talks about building racks and designing the networks, and then creating and deploying a blueprint. And this order is relevant because this is the order that you would typically design and then deploy a blueprint data center with. As I mentioned, we're going to be automating the design of AI clusters. That turns out to be all about logical devices, the racks, and the templates. And then, of course, the template is used to deploy the blueprint. And you can stamp those out again and again. So, as I mentioned, the design phase is certainly customizable. But rather than having you have to point and click your way around that, you can automate things with Terraform. And we've automated all of these examples for you. So let's have a look at that. Let me just go into racks first of all and assure you that this is a standard out-of-the-box Apstra instance. There's nothing in here, nor in any of the templates, that doesn't come out of the box with Apstra. What we're going to see is that there's a whole bunch of templates related to AI cluster networks that are in here, and we'll talk about some of the nuances and differences in that design and how that is important to AI use cases such as model training. So now that we've got this up and running, one of the things that we need to do is actually get this example Terraform HCL configuration onto the laptop. So I'm going to use GitHub Desktop because it's a nice visual tool. It makes sense to demo from it. I've already logged into my GitHub Desktop instance, and if I just start typing some of this stuff, you can see I can easily come and choose to clone the repository that I was just showing you in the browser. So now all of that stuff is downloaded to my laptop. I happen to have Visual Studio Code installed, and this handy button will open it up just like that. I'm going to just make this instance of Visual Studio Code a little bit bigger to match my video. And you've got all of the examples. We're going to only need to look at the AI clusters bit of this. Now, I'm not going to go into all of the HCL configuration. The one thing that you do need to see and actually change is the place that you're going to point Terraform to. So we need to change the username and password to match what we got from Apstra Cloud Labs, and we need to change this Apstra URL as well. Let's go back to our instance of Apstra here, copy the IP address and port number, and then go back into Visual Studio Code and replace that Apstra URL placeholder with this. Okay, so from there, I'm just going to save the file and close this down. One of the things that you can do in Visual Studio Code is open up a terminal. Let's go into the AI cluster subfolder. From here, I'm going to do a Terraform init. That'll just make sure that I have the most recent version of the Terraform provider for Apstra. After that, you can, if you would like to, do a Terraform plan. It's an optional step before you apply. And it looks like I have an error in my provider file. Right, so one of the things that I happen to have in my password that I need to change is that little symbol there. It's got to be URL encoded. I'm going to go back into here and just resave the file. Didn't expect that, but that's a live demo for you. Okay, after that, it's happy, and it says that it's found 53 resources to add, nothing to change, nothing to destroy, of course, because we haven't applied anything yet. So that all looks good. Now, let's do a Terraform apply. And while we're doing this, what I wanted to show is how fast things happen in Apstra at the same time. So I've got these templates up in the back here, right? So watch those templates all change as many of the templates are now put into Apstra with this Terraform apply. Just have to answer yes, I'm ready to go. And boom, you can see all of that happening. And then in the browser over here, you can see how quickly all of these things appeared. Now, what's pretty neat about all of these examples of, for example, different sizes of GPU clusters, some large ones, we've got certainly quite a bit here in terms of 256 DGX. Those are NVIDIA servers with the H100 GPUs or the A100 GPUs. What you'll see of these examples and the ones like it at smaller sizes, like that guy and that guy and that guy, these are the back-end training fabrics that are used for model training. And when you're running an Ethernet training fabric, you've got RDMA over Converged Ethernet. We call it RoCE for short, RoCE. And that RoCE fabric has a very special design recommended by NVIDIA to drive the maximum performance and job completion time, and networking performance drives job completion time, of course, in your network. And this special design is called a rail optimized design, where rail local traffic can go over fewer hops because these 64 DGX servers actually have an internal switch to it between the GPUs. So you don't need to go, for example, from GPU 1 to GPU 2 within the same server across a top of rack leaf switch. It's able to do that just inside of the server. And it has a special feature of the rail optimized design in the newer versions of NVIDIA Nickel. This feature is called PXN, and it allows even further rail local optimizations, such as when two different servers are talking to each other, you'll have traffic that doesn't have to go over the spine network. And we can explain that in just a second. But I wanted to kind of go into one of these clusters and show you what it looks like, of course, and then sort of explain some of the rail optimized design from there. You can see the option to expand things and whatnot. This happens to be using a certain rack type. Rather than just click that, I'm going to actually go into all of the racks and show you all of the different types of racks here for the storage fabrics, for the management front-end fabrics. And the rack that I was just looking at is this one right here. Now, this does not look like a typical data center rack. And in fact, this is not a physical rack design. In this case, in order to accommodate for NVIDIA's rail optimized design, what we've done is we've built a custom rack type inside of Apstra for what we call a stripe. Or in other words, it's a group of 8 leaf switches. And why 8? Well, because you have 8 GPUs on the server. And like I said, those servers that you see here, the 16 of them could be, DGX, or they could be HGX based, which just means you can get them from, like, say, a Dell or a Supermicro or someone else. And they follow the same pattern of having that internal switch and 8 GPUs, and effectively the same build out of hardware. Now, what you'll see in this design called Rail Optimized is that the GPU1 inside of the server in this special network for the GPUs to interconnect, again, this is for model training, or sometimes called the backend network, you'll see that these 8 different GPUs are individually cabled up to the 8 different leafs inside of this stripe. And this is, of course, not a typical data center design. In a typical data center design, what you'd expect is probably many fewer ports on each server, and you'd expect those ports to go up to one top of rack switch, or sometimes aggregated to a pair of switches that might be connected with ESI lag. So this is, of course, very different. In these IP fabrics, what I mentioned that PXN feature is able to do is when you have traffic, let's say, going from GPU 1 of this server to GPU 1 of the second server, they'll, of course, be able to, since they're cabled up to the same leaf, be directly accessing each other with just a single hop across that top of rack leaf switch. Now, what if, let's say, GPU 1 of this server needs to talk to GPU 2 of the other server? Well, you'd expect that, you'd probably expect, I think, that you'd go from this leaf switch here to a spine switch and then down to the leaf switch with which, GPU 2 is connected. Now, that might make normal sense, but as I mentioned, this special nickel feature from NVIDIA called PXN allows this server to understand the overall topology, and it will use the internal switch in the server to pass the traffic from GPU 1 to GPU 2 locally, and then it'll send it to the top of rack switch representing all of the GPU 2s and then down to this second server. The cool thing about that is, it really optimizes for latency, and performance is really key inside of these use cases because, of course, these servers are very expensive, hundreds of thousands of dollars. Each GPU is very expensive, right? Tens of thousands of dollars. And to the extent that your GPUs are sitting idle, wasting time, waiting for the network, you're losing return on investment, of course, right? So this is why, the network may not seem like the most important thing to AI clusters. You'd think it's got to be the GPUs and all of those servers. They're such a big expense. But if your network is holding back the performance of your model training and your GPUs, what good are your GPUs to you? They're not, right? This is why the network performance is really key when you're designing AI clusters. And with these examples, you'll be following the best practices in starting from a foundation that is strong to assure the best performance possible. When would traffic be going through the spine switches, you might ask? Well, let's go back to look at the template again, and I'll just pick on this smaller cluster because it's a little bit easier to see. One of the times when you would see these different groupings here, which we called stripes of different, 16 different servers or 8 leaves, of course, if traffic has to go from one of these servers to a server in a different stripe, then, of course, the traffic will cross over the spine network. And when it's crossing across the spine network, again, there's things that you want to design for in the spine network, such as dynamic load balancing and network congestion management protocols like DCQCN, which is a combination of ECN and PFC. You can go and read about these things in glorious detail in the Juniper Junos documentation, and we'll talk about automating some of those configurations in another video. But for this video, I think I'm done explaining the rail optimized design that is recommended as a best practice from NVIDIA. And you've seen also how simple it is to use Terraform and take all of these examples for these things that I hope you dig into yourself and go and apply them into an instance of Apstra that is really accessible to anyone. So Thank you for your time and trust in joining me on this quick demo journey. Again, this is James Kelly from Juniper Networks. Reach out to us at Juniper if you're building AI clusters. We'd love to help you.